Now we talk about Chapter 2, Review of Signality and Signal Representations. So this is just, review of what you have learned in 315 class, Signal and Systems. So as we know, there are many different types of signals, continuous and discrete, analog and digital, periodical and non-periodical, deterministic and random, finite energy or finite power. And later we are going to show the examples for all different kind of signals. So first of all, continuous signal. Almost all the signal we met in our real life, they are continuous signals, like power, right, current, temperature. So this is example. We have a sinusoid signal here. So we can find in time it's continuous, right? In amplitude it's also continuous. So this is a example for continuous signal. So on the other hand, we also have discrete signals. We can only have those samples at every period, capital T. So this figure shows a discrete signal. We only have some pulses, right? So generally, discrete signal can be obtained by sampling a continuous signal. Okay, analog signal. So analog signal, similar to continuous time signal, it's continuous in time and also in amplitude. And we use analog circuits to process analog signal. Digital signal will be totally different from analog signal. So from this example, we can find the amplitude. You only have several different choices, right? In time, it's also discrete. So digital signal will be discrete in time and discrete in amplitude. Okay, this slide shows a periodical signal. So we can find a triangle wave. This triangle pattern repeat, right? Every period. So we call it periodical signal. And once we know the period, we know, right, how long it will repeat itself. On the other hand, we have a non-periodical signal. So this one does not have any pattern, right, repeat itself. So it's a non-periodical signal. And the random signal, such as noise, speech, music, generally they are non-periodical. Okay, deterministic signal means, right, you know what's going on. For example, this sinusoid signal, if you know the amplitude, the frequency, and the initial phase, you can tell what will be the exact value at a certain time. For example, in the power line, right, the electronic signal is sinusoid. And more general, we have random signals. So we have no idea what's going on, totally random. So for random signal, we care much more about the statistic parameters of a random signal, such as power, mean value. Okay, then we talk about finite energy signal and the finite power signal. This is a finite energy signal. We can find it's an energy signal. And the next one is a power signal. If you calculate the energy of it, it will be unlimited. Okay, after we're talking about signals, we talk about systems. So system, we have linear and nonlinear. Linear system follow two rules. One is called additive. So it means you have two signal addition to this as input to the system. The output also will be this addition of the two outputs from previous input signals. Second, we call it scaling. So if your input signal is amplified by 8 times, the output will be amplified by exactly same times A. So this kind of system will be called linear. Time invariant and time varying. So if your system is kind of fixed, no matter what time it is, the input will give you the same output. We call it time invariant. On the other hand, it will be time varying, right? So your system is time changing. Even you have same input, according different time, the output may be different. Okay, now we talk about a very important thing in this chapter. We call it Fourier series representation. So we are going to discuss trigonometric Fourier series. So that means use sinusoid, right, to present a periodical signal. Then we talk about Parsval theorem of frequency transfer function, steady state response, and Fourier spectrum. Okay, Fourier series. As we mentioned before, we have periodical signal, non-periodical signal. So for a periodical signal, ft, this one can be written in infinite summation of different harmonics. So in 315, we also learned, right, for a periodical signal or time-limited signal, it can be expressed by unlimited summation of different harmonics. So EJN omega 0t will be your harmonics with different fundamental frequency, and Fn will be the amplitude of this harmonic. Now we talk about how can we calculate, right, this Fn, this amplitude. This amplitude Fn we also call it Fourier series. Okay, so here this equation shows how can we calculate Fn. So generally we have an integral, right, from t1 to t2. Ft will mixed with complex exponential e to minus jn omega dot 0 dot t, and normalized by the time duration. If your signal is a periodical signal, we are going to just integral in one whole period and normalize by this period. Okay, and we are going to use examples 2.7.1 to show how to calculate a given signal's Fourier transform, Fourier series. So that is one format of Fourier series. We have another format. So equivalently to the previous Fourier series expression, we can also use sine and cosine instead of complex exponential. So here we have an, right, cosine n omega dot t, and bn sine n omega dot t. So those are other, right, harmonics, not complex anymore. They are real signals. A0, an, and bn will be real constants in this equation. So here is how can we calculate an, bn, and a0. So similar to previous equation, but we change complex exponential to sine and cosine. If the signal is periodical, we are going to change the lower and upper bound to minus t over 2 to t over 2, normalized by the period, capital T. A useful example you can take a look will be example 2.9.1 from our textbook. So here just a review of Phasor we have learned before. So in 210 class, right, and maybe in 315 class, we all talk about Phasor. Phasor is a time domain element. So it's periodical, right? Frequency will be omega 0, and it's complex. Complex means we have real part and imagery part. So it has its amplitude. Here, A's amplitude. It has frequency and phase. Okay, next slide is a Phasor so we can find this is a vector, right? The length will be a, and the phase angle will be omega 0t plus theta. So we have real and imaginary parts, we have amplitude and phase. Okay, Euler equation can connect complex exponential with sine and cosine. So I would like you to practice by yourself. Try to express this sinusoid signal in terms of phasors. Okay, so Parsval theorem. Previously we talked about how can we calculate signals power, right? So Parsval theorem gives us how can we find a given signal's power in time domain, and also by using Fourier series. Okay, frequency transfer function. So frequency transfer function can determine a linear time invariant system. All those A and B are constant coefficients. So typically, a LTI system can be expressed by its frequency transfer function. We are going to talk about more details later in chapter 3. Okay, so once we have frequency transfer function, we can define steady state response. So look at the right part of this equation. We can find the Fourier series, right, for your input signal ft. So the output gt will be the linear combination of your input with your frequency transfer function. Okay, so after we talk about systems, we go back to some special functions, some special signals. We are going to talk about impulse signal, unit step signal, and rectangular signal. So the first one will be impulse function. For impulse function mixed with another function, calculate the integral. You are going to extract that specific point from the given signal. So the condition is T0 will be fall in those two boundaries. Second property, the area under impulse function is 1, otherwise will be 0. Okay, impulse function is even symmetry, so delta t equal delta minus t. And for scaling property, delta at will equal 1 over a absolute value delta t. Example 2.18.1, example 2.18.2 will show how to use those properties to solve some problems. So impulse functions, Fourier transform or spectral will be a flat line. Singularity functions, second one will be unit step function, and the third one is rectangular function. This picture shows a standard rectangular function with y is 1, height also 1. And this one is a general one, so it can be shifted to T0, right? The duration can be changed to tau, and amplitude is A. Okay, the last one will be impulse response. So when your signal is impulse signal, this one goes through a LTI system. The output, we call it impulse response. So for LTI system, impulse response will tell us many important properties of this system.